discussing a paper we just published, Inverse Science, flipping the process of discovery on its head. AI is going to change the way we do science fundamentally, and it's actually going to turn around or flip the process of discovery on its head, literally. Instead of starting in traditional science, the way you work is, or legacy science, if you will, is you look at the world, you observe data, you then formulate the model, and then you come up with a hypothesis and potentially an explanation. You also test the hypothesis in experiments. The way, what the novelty that AI is going to bring, there's two fundamental things that AI is going to bring to the table. One, the actual question you're going to ask yourself as a scientist is going to be much more, what kind of data do I need to train my model to solve a certain problem? So you're going to think a lot more about the data. And second, AI is going to allow iteration at scale, rapid iteration at scale, which means that we can try many, many more things much faster, and more importantly, also we can validate them in simulation. So with those two innovations, we believe that science will actually leapfrog where we are today, and we will have a much accelerated way of doing science and engineering. So I want to illustrate this with an example, which is also illustrated in the essay. And the example is in material science. I'm using Starship and the heat shield for Starship as a test case. So the heat shield of Starship is one of the big problems in re-entry or for re-entry. So if Starship wants to actually become a Mars-going entity, or at least an out of orbit going entity, so we want to send this thing out in space and bring it back, we need to find a solution to deal with the massive heat fluctuations or temperature fluctuations that Starship's going to go through while re-entry into the atmosphere. So we're going from almost absolute zero, a few degrees of Kelvin, into the thousands of degrees of Kelvin when the Starship re-enters. For that, we need a heat shield. The heat shield is a problem, and that is a scientific problem as much as an engineering problem. So what we're going to do in traditional sciences, we're going to try to see what happens. So we're going to launch these Starships en masse, see what happens, and then potentially learn something from the data. In the new world of AI, what we're going to do two things. First, we're going to think about the actual data that we need in order to train the model to give us a solution. So we're going to think about the data, and the data might actually not have to do anything with Starship re-entry. It could be that we're looking at subatomic particle behavior from Large Hadron Colliders. This is beyond my pay grade, of course, but that's exactly what the scientists of the future will be thinking about. He'll be thinking about, okay, what kind of data could I potentially use to train my model to come up with a solution? And I think it's really paramount. This is a fundamental shift in the way we approach science and, of course, engineering, because here the reverse engineering comes into place, or the inverse engineering, where we start with the property. This is what we need. We need Starship to re-enter. Now, can you come up with a solution for that problem? What kind of data do we need to train the model with? The other big advantage that AI is going to bring, or maybe this is the first point, this inverse discovery, that is just a change in the process. But the big advantage that AI is going to bring is that we're going to have iteration at scale. So what our AI models will be able to do is they'll be able to try many solutions at scale. So the lone scientist tinkering in his lab or even SpaceX blowing up starships on a weekly basis, that can be replaced with AI that can iterate at scale and, most importantly, test at scale. So what the scientist is going to do is not just going to develop a data architecture, but also an eval structure. Eval is key in any kind of AI context. We've learned that already now. I think where we stand right now with AI research is, I would say, if I go through the labs here in Silicon Valley, the word that I hear most is eval. Eval, eval, eval. What kind of eval? Evaluation. Eval is short for evaluation. What do we need to evaluate the model? Because the models themselves, they need to know whether they are on the right path or not. There's also the concept of reward shaping and reinforcement learning, which is a sort of a specialized case of eval. The problem fundamentally is the same. Like, we need to understand how to tell the model when it's on the right path and when it isn't. So back to the science question, the scientists of the future will be occupied a lot more with questions of data architecture and evals and reward shaping for the model to train and find a solution that potentially could solve the problem. In the case, let's say, in this SpaceX problem, it would be the what kind of tiles, what kind of materials can be used to solve this particular re-entry problem. So to summarize, this essay is in the series of essays that we occasionally publish about what we think is relevant for our business. Also, we've published essays in the context of other things like philosophy. We've even published a novel, Chronopunk. So we do these things occasionally. I think what's important in this particular essay is really the emphasis on the potential that this new AI world brings. We got inspired by actually Terence Tao, who was talking to OpenAI about the new kind of math that is possible with AI. And I think Terence is on the right path. He's emphasizing the ability to iterate at scale and also eval at scale. So iteration and eval at scale are the two key components that will eventually propel this new kind of science that we're embarking on right now, thanks to AI. Thank you.